Hello, namaste. My name is Jairam Bista. Here is my project, Seismic Monitoring and Early Warning Systems. It's the project based on IoT, and there have been used almost 500 IoT nodes, which are the networkings, which make the networkings to perfect out this system. Here in the slide two, it's about the presentation agenda. Let's move to slide four, problem statement. The 2015 Gulf earthquake caused about 9,000 deaths and over USD 7 billion in damage, exposing Nepal's high vulnerability to major seismic events. However, the country still lacks real-time automated warning systems with limited sensor coverage, high data latency, and no structural or secure monitoring infrastructure. Here in the slide five about the project objectives SMUs. The SMUs project aims to build a nationwide real-time uh, seismic monitoring and early warning system by deploying almost 500 IoT sensor nodes across all 77 districts, ensuring alerts within 10 seconds and structural monitoring of critical infrastructure. It also delivers secure cloud-based NIST 2.0 compliant data services for government, emergency response, and research applications. Slide 6, sensor hardware design. The sensor hardware combines high precision seismic, environmental, and structural monitoring components, including accelerometers, geophones, GPS timing, and inclinometer units for accurate ground and structural movement detection. All sensors are integrated with low power is computing, solar power autonomy, and hybrid LoRa full C connectivity to ensure continuous real-time operations in remote conditions. Slide 7 is about the network architecture and connectivity. The SMU's network uses a layer architecture where sensor nodes detect seismic activity and transmit data through LoRaWAN, fuzzy or satellite links depending on terrain. Data is processed in cloud platforms like AWS and Azure, then delivered to dashboards and emergency systems with latency optimized by region. Next slide 8 is standard communications protocols. The system uses standardized IoT and industrial protocols such as MQTT, COAP, LoRaWAN, and NB-IoT for instant sensor communications and control across constrained and wide area network. Security, interoperability, and precision are ensured through TLS to TLS encryption, CVR encoding, OPC UA integrations, and high accuracy time synchronization using IE 1588 PTPv2. Slide 9, it's about the algorithmic flow. This flow chart illustrates a sophisticated seismic monitoring system that uses high precision sensors to detect P wave bounces through STA/LTA ratio analysis. Once a system potential event is triggered, the system secures data with SMAC as SA-256 signing and MTLS encryptions before transmitting it via MQTT to a cloud-based stream processing pipeline for real-time validation across multiple stations. The slide 10, again, algorithmic flow. The flow chart outlines an advanced seismic event processing pipeline that uses 1D CNN inference on SageMaker's CPUs to classify waveforms and filter out noise. For high probability events, the system estimates magnitude using a random forest model and calculates the epicenter via SQ inversion using the IASP91 Nepal velocity model to trigger alerts if magnitude and system thresholds are met. Here in the slide 11 again, it's about algorithmic flow. This final stage of the logic flow validates detected seismic events by ensuring at least three independent iterations confirm the signal and checking against a 120-second day duplication window to prevent redundant alerts. Once verified, the system assigns a severity level based on magnitude calculates as wave arrival times for specific districts and executes a fan-out dispatch to various emergency alert platforms before achieving the record. Slide 12, Cloud Platforms and Analytics Pipelines. This slide represents the end-to-end system integrations pipelines that flows from sensor nodes through gateway into a multi-cloud architecture. AWS serves as the primary processing platform, while Azure provides active failover capability, and on-premise OpenStack system ensures operational continuity cloud during cloud outages. Real-time data is processed, stored, and visualized through dashboards for government agencies, emergency responders, and the public. Alerts are disseminated via SMS, mobile applications, sirens, and broadcast systems. This architecture ensures high availability, scalability, and resilience for national level early warnings. Slide 13 is about the cloud platforms and analytics pipeline. Again, the system uses a hybrid cloud architecture with AWS as the primary platforms and Azure as a secondary failover, enabling real-time data ingestions, processing, and machine learning for seismic analytics and open-premise OpenStack cluster in Kathmandu provides dependent air-gap alerting capability to ensure continuous operations even during cloud outages. Slide 14, uh, slide 14, machine learning models, cloud forms, and analytics pipeline. The system uses 1D CNN model to accurately detect keywords with high precision and recall, enabling fast and reliable earthquake signal classification. A random forest model then estimates earthquake magnitude within seconds of detection, achieving low error for rapid early warning decisions. Slide 15 is about the security frameworks. The SMU's security framework ensures a strong device authentications, encryptions, and trusted communications using X.509 certificates, PPM, dash-based key storage, and modern protocols like TLS 1.3 with AES 256 encryptions. It also protects the system through secure boot signed OTA updates, network segmentation, and continuous intrusion monitoring align with NIST CSCF 2.0 and IC 62443 standards. Slide 16, real world data use cases. The SMUs data supports seven key applications, including early warning, structural monitoring, hazard mapping, emergency response, insurance, risk assessment, power safety, and open scientific research. Slide 17 is about 5-year deployment plan and budget. The SMU's deployment will scale from a 15-node pilot in 2025 to full national coverage by 2027 to 2028, followed by optimizations in 2029 with a total protected budget of Nepali rupees 292.6 million. Next slide 18, project risk register. The project risk register identifies key operational risk such as connectivity, security, and power failures, and mitigates them through redundancy, multi-layer security, and VAC energy systems. Let's move slide 19, conclusion and impact. Here, this is the last one slide. The SMU's project demonstrates strong technical capability, financial sustainability, and nationwide institutional integrations to reduce Nepal's long-standing seismic risk and disaster impact. Thank you so much. Here is the references I took from different journals, which are here below. Thank you so much. So here I complete my uh, presentations. Thank you so much. Good night.